All right, so the problem of the day last night was pretty tricky. I'm sure most of you guys saw that. So let's take a look at problem 1. Problem 1 asks you to compare a Newman projection to a bond line formula. So let's first try to compare apples to apples rather than apples to oranges, right? So what I'm going to do is redraw that Newman projection using the bond line formula. So if you think about this, right, imagine that we're looking down this bond through here. You can see the front carbon has an ethyl group and methyl group coming off of it. The back carbon just has a methyl group coming off. You guys see that? All right, what would we name the molecule on the left? Yep, 3-methyl pentane. All right, what would the molecule be on the right? What would its name be? 2-methyl pentane. All right, so if we're comparing these, they're both methyl pentanes. They both have the same molecular formula, but in one, the methyl group's attached in a different position. What do we call it when we've got two molecules with the exact same molecular formula that are connected differently? Yeah, constitutional isomers. What does it mean if it's non-isomeric? A lot of people were asking me about non-isomeric. Yeah, absolutely different molecular formulas. So we're comparing completely different things. So these are definitely isomeric. They have the same molecular formula. They're just connected in a different way. All right, part B. Again, I don't like comparing apples to oranges. Let's compare apples to apples. So I'm going to redraw this chair structure as a 2D bond line. And if we think about this carbon over here, it's a dash, and this carbon would be a wedge, right? So in this case, we've got a trans dimethyl cyclohexane, right? All right, if we look at our stereocenters, we've got a stereocenter right here. And if we look over there, the stereocenter is exactly the same, right? Our methyl group's a wedge in both cases. But let's look at the stereocenter on the top. It looks like we've flipped our blue stereocenter. So they're opposite of one another. So what do we call a pair of molecules where some, but not all of their stereocenters are flipped? Diastereomers. Does anybody notice anything unique about the molecule on the right? It's drawn really well. Yeah, that was my job. Thank you. Anything else? It's meso. So in addition, the compound on the right has an internal plane of symmetry. It's meso. Therefore, the compound on the right is achiral. The compound on the left, on the other hand, does not have an internal plane of symmetry, so it is chiral. That wasn't a part of the question, but it was something kind of unique that you could think about. This one is not chiral. It's meso. And this one is chiral. Oftentimes when we're talking about molecules that are not chiral, we just call them achiral. Yep.
Does it matter where your line of symmetry lies? Like whether it's horizontal or
Yep, you can put your internal mirror plane wherever you want. You just have to make sure you have the exact same groups on the opposite side of that mirror plane. Yep.
So internal plane symmetry means it's meso?
Yes. If you've got stereocenters and an internal mirror plane, it means you've got a meso compound. Yep. All right, the next one, if we're looking at these bond line structures, it's a little bit tricky. We've got a hydrogen pointed out, a chlorine going back, and then a CH3. And then we've got a CH3 pointed back here. So I'm just converting these to bond line structures. And we've got a chlorine here and a hydrogen pointed back. So we need to identify our stereocenters. So we've got this blue stereocenter here. What's highest priority? chlorine. So I'd label this as 1. And then we've got a tie, right? We've got this carbon here, and we've got this carbon over here. Which one's going to be higher priority, the methyl group or the carbon on the right? Carbon on the right, because the carbon on the right has an attached chlorine. The methyl group just has attached hydrogens. Chlorine beats out the hydrogens. So we'd label this as 2, and then we'd label this as 3. So we can go through and we can say, all right, this is going to the left, but where's our lowest priority? It's forward. So we'd label this as RS. R. If our lowest priority were pointing backwards, it would be S, but because it's pointing forward, we label it as R. So let's do the same thing with this one. We've got a stereocenter right here. We said chlorine's 1. This would be 2. Methyl group is 3rd. Our lowest priority is pointing backwards, so will that be R or S? S. Okay? We can do the same thing with these ones. So let me draw this one underneath. Whoops. We've got a CH3, got a chlorine pointed out here, hydrogen going back, CH3, got a chlorine that's a wedge, and we've got a hydrogen back there. All right, so let's look at our blue stereocenter. Did we flip it or keep it the same from our original one? So you see our chlorine was pointed back, but now it's pointed forwards?
Yeah.
Looks like we flipped our stereocenter, right? So without even assigning priorities, we could say that the blue one's going to most likely be what? S. We can go through and double check just to play it safe. So I'll label chlorine 1, this one 2, and 3, and we can see that it's rotating left, right? This last one, got a stereocenter here. We go 1, 2, 3. Is that R or S? S. So this one would be our SS. The one on the left would be our RS. And then last but not least, we've got our CH3. Hydrogen pointing forward. And our H. So we can identify this blue stereocenter. We go 1, 2, 3. We're going to the left, but our lowest priority is pointing forward. So what would this be? R. And then over here, we can label this stereocenter. We've got chlorine as 1, this carbon as 2, this carbon as 3. Lowest priority is pointing forward. Would this be R or S? R. All right, so we've identified our RS compound, our SS compound, and our RR compound. These are all related to each other, but they have a different layout in three-dimensional space. So now the question is, which one of these is our meso compound?
First one.
Ah, this one's tricky. So let's take a look at this. I'm going to label this one as compound A, B, and C. Let's imagine A doing a flip, or sorry, a rotation. All right, so what I'm going to do is I'm going to take this methyl group, I'm going to rotate it all the way over here. I'm going to take this hydrogen, I'm going to rotate it, and so we're going to go completely to a new staggered conformation, right? So our back carbon's held static, our chlorine's pointed out, our hydrogen's pointing out, we've got Me, and now we've got a cis Me, our chlorine's back here, and got a hydrogen over here. So if you look at it this way, our front carbon is a mirror image of our back carbon, right? Is there a light flickering, or am I going crazy? Okay. Front carbon is a mirror image of the back. Therefore, this is meso. meso compounds are achiral. So even though they do have stereocenters, they're not optically active, they are achiral. If we look at B and C, do you think B and C are chiral compounds? Yes. If you have stereocenters, but you do not have an internal plane of symmetry, you are chiral. So that's one good way of checking, is always check for meso compounds, ones that have an internal plane of symmetry in them. I know it gets tricky, but let's briefly go back and review a little bit before we go into our in-class activity. So a couple days ago, we made this flowchart where we said isomers have the exact same molecular formula, but within isomers, we have two different classes. We've got constitutional isomers that have different connectivities, and then we have stereoisomers that have the exact same connectivity, but a different three-dimensional layout. Now what we can do is we can break these stereoisomers into two new classes. And what were the two classes of stereoisomers that we were dealing with? Yeah, diastereomers and enantiomers. And enantiomers. All right, what was the defining characteristic of an enantiomer? Yeah, non-superimposable mirror images. What about diastereomers? Yeah, exactly. So one thing we could say is that they are not mirror images. And then we could say that some, but not all, stereocenters are flips. Versus enantiomers, where all stereocenters are flipped. Okay, so now we can subdivide our stereoisomers into diastereomers and enantiomers. On the handout I gave you guys the other day with assigning R versus S, you'll also see that there's some other classes called rotamers and conformers. That's essentially the Newman projection rotation and the chair conformation flip. So if you are able to lock things in different chair conformations or different rotational conformations, you can run into classes of diastereomers as well. What I'm primarily concerned with is you guys knowing the difference between diastereomers and enantiomers. So if I give you a pair of molecules, I might ask you, are these constitutional isomers, are they diastereomers, or are they enantiomers? Or I could say, is this compound meso, meaning are they identical? Okay, so let's go back to our chirality portion too, and I wanted to add one last thing on here. So I said a chiral molecule is one that is non-superimposable on its mirror image, and then I gave an example where if you draw the mirror image, you're showing its hypothetical enantiomer, and in this case it was non-superimposable. And then we said we can tell these apart by using plain polarized light, and so on and so on, and we gave a nice example there. But let's make a little bit of a cheat here. Let's do a quick way to spot a chiral compound. First thing is, does it have a stereocenter? Let's do one or more. One or more stereocenters. If we say no, then it's probably not chiral. I'm sure you guys have taken enough chemistry classes to know that there's an exception to every rule. And that's why I said probably, not absolutely not chiral. There are some weird forms of chirality called axial chirality that we're not going to spend very much time on. Next week when we come back, I'll show you an example of that. So if it doesn't have a stereocenter, chances are it's not chiral, but it's not an absolute 100% certainty. If we say yes, there is one or more stereocenter, then we need to ask ourselves another question. Is there an internal plane of symmetry? Why are we asking about internal planes of symmetry? Yeah, exactly. If we say yes, then the compound is meso. And are meso compounds chiral? No, it is achiral. If there is no plane of symmetry, then the compound is chiral. So this is one nice, quick and dirty way of determining whether or not a compound's chiral. The absolute definition of chirality, though, goes back to the idea of drawing a hypothetical mirror image and seeing if it's superimposable. This is the quick and dirty way. If you spot stereocenters but no internal plane of symmetry, then it's usually going to be considered chiral. All right, so what we're going to do with the rest of the period is I've got an in-class activity. And this is taking it to the next level. I'm giving you the name. And you may notice on the name it says 3R. What do you think the 3R means? Yeah, that third carbon has a stereocenter. And the stereocenter on the third carbon is R. So I want you to figure out how to draw 3R, 3-methylhexane. And then for the next one, we've got 2R, 3S, 2,3-dichloro, 1,1-dimethylcyclohexane. So in that one, second carbon's R, third carbon's S. Then we've got another example for C. And then if you guys feel like, wow, this is super easy, throw me something hard. Problem D is tricky. You can spend a little bit of time working on problem D. Problem D is the hardest one on here. On the back page, you can go ahead and cross out these two. They're Fisher projections. We're not going to cover Fisher projections right now. We're going to cover them eventually, but for right now, don't worry about those. Try to first determine whether or not the molecules are chiral. So in this case, they ask if they're optically active. That's another way of asking if they're chiral. Question 3 is for you to first label the stereocenter as R or S. Then I want you to determine what percent is the correct enantiomer given the data, so that alpha sub D is the given value, and we measured it to be negative 1.7. And then the last portion is to draw the enantiomer. So I would get together in a group of about 3 or 4 people and start working on these, and I'll come around the room and try to help you guys, but try to help each other as much as possible. All right, compound A, we've got hexane. How many carbons are in hexane? 6. So I'll go through and do 1, 2, 3, 4, 5, 6. We've got 3-methylhexane. So the question is that methyl group a wedge and is a hydrogen pointing back? Or is the hydrogen pointing forward and the methyl group going back? So when you're stuck between 2 possible options, draw them both out and then decide. So I'll let you guys get started with that if you were getting hung up on this. I know that's not a lot of help, but it gets you at least started.